For this first one here, we have a group of positrons, which are a type of antimatter. They're just positively charged electrons that are being destroyed by some regular electrons, regular negatively charged electrons. And we want to know what the total charge of the electrons was that destroyed them if the positrons had a charge here of 2.24 times 10 to the negative 18th coulombs. Well, for this one, we know that charge is conserved. A net charge cannot be created or destroyed, so the electrons must have had the same amount of charge, just negative 2.24 times 10 to the negative 18th coulombs, in order to destroy them, because a net charge cannot be created nor destroyed. For this next one, we have a diagram showing a neutral object before and after a charged object is brought near. And we have two questions here. The first is the neutral object a conductor or an insulator? So we're looking at the movement of the electrons, how drastic that movement is. And we see here the electrons are initially all near their nuclei, near their positive charges. But after that object is brought near, all the electrons are gathered around this spot. We have nuclei that are just positively charged that have no electrons around them. So this object must have been a conductor because of that drastic movement of an electron. The insulator would not allow that to happen. Second question, is the charged object positively or negatively charged? Well, the electrons move towards it, which means this must be a positive charge because it attracted the electrons and caused them to move to the right. For this next question, we have to draw the diagram of a neutral object, in this case an insulator, when a charged object is brought near it. Let's first look at this charged object. It is overall a positively charged object because there's more positives than negatives. So let's think about the movement of the charges in our insulator. So the first thing we can do is we can draw the positive charges in the exact same spots. We know that positive charges won't move. Okay, we don't have movement of the protons when a charged object is brought near. The electrons, on the other hand, will move towards it, but because it's an insulator, they have to stay relatively close to their nuclei. So they'll shift all over to the right-hand side, but we see that they all kind of stay near the nuclei that they originally were with. We just have a slight shifting of the electrons to the right. For this question, we have a situation over here where a positively charged object A touches a neutral conductor, object B. That positively charged object is then removed, and then B is brought near another neutral object C, which is touched by D, and then D is removed. And we want to know the charge on the various objects at each point in time. So let's just take it one step at a time. Start with this first question here. What is the charge on object B after it's touched by A? So object B was initially touched by A, and A was a positively charged object. And so we always want to think about what are the electrons going to do. And the electrons in B, they like that positively charged object in A. And so what they're going to do is they're going to transfer from B to A. And so what's going to end up happening is B is going to become positively charged because it lost electrons. They transferred to A through the process of conduction. Okay, this is charging by conduction. Question B asks what's the charge on A after it's touched by object B? And so we know that A is going to gain some electrons, so it's going to become less positive. However, it won't actually get to the point of being neutral, and it certainly won't get to the point of being negative, because what's going to happen is as B loses electrons to A, B is going to become more and more positive, and so the electrons are going to actually be less likely to transfer to A, because A is not as positive as it was before, and B now is relatively positive, so the electrons are a little bit happier being here over with B. All right, and so even though A will gain some electrons, it's just going to become less positive than it was before. Part C asks about the charge on object C after object D is removed. So let's think about that interaction here. So we now have a positively charged object B here brought near C. And what that does is that causes a shift in the electrons within C. It causes C to become polarized because C is a conductor and the electrons are going to travel to the left side of that conductor because they're attracted to object B. When D touches them, what ends up happening is D sees that the electrons in D see that this side of C, this right side of C, is relatively positive because it's been polarized. And so electrons are actually going to transfer from D to object C because ultimately they're trying to get closer to this positively charged object here, object B. And so when D is removed, that connection is broken. C is left as a negatively charged object and B obviously is still positively charged. For this next question, we are bringing a negatively charged piece of PVC pipe near a neutral hanging ball of aluminum foil here. And initially, the PVC pipe is attracted to that ball, and we want to know why that happens. And the reason for that is simply because of polarization. This negatively charged ball causes the electrons in the ping pong ball to shift away from it because they're repelled, and that leaves us with one side of the ping pong ball being more negatively charged, one side being more positively charged. And that polarization ultimately leads to an attraction because this positive side is closer to the PVC. The second question here asks why the ball was repelled then by the PVC after touching the ball. And what's going to happen is when these two objects finally touch, we're going to see a transfer of electrons. So at that point of contact, when our PVC and our ball are touching, electrons are going to transfer from the PVC to the ball. This is conduction right here. That's going to leave both objects negatively charged, and therefore they will repel. For this next one, we have two oppositely charged objects. They're initially some distance away from each other, and they accelerate towards each other. We know the initial force between them is this quantity here, F, and we want to know how much force they exert on each other when they're half the distance apart and when they are 1/5 the distance apart. So this is one where we're going to set up our original situation and our new. In both cases, we're thinking about Coulomb's law. Fe equals k q1 q2 over r squared. So initially our force is just F. We don't know q1 and q2. They're not going to change those, so I'm just going to leave them as q1 and q2. And I'm going to say that initial distance between the two objects, one positive, one negative, is just going to be r. Okay? So that's our original equation. For part A, our new equation is going to be what happens when they are a distance of r over 2 apart. So I'm going to say F prime equals k q1 q2, because the charges haven't changed, over r over 2, that quantity squared. And so that becomes k q1 q2 over r squared over 4. To get rid of that double fraction, we're going to multiply top and bottom by 4, and what we're left with is F prime is equal to 4 k q1 q2 over r squared. We see the difference here is just that 4 on top, so that means that our new force is going to be 4 times our original force. And that makes sense given what we know about inverse square laws as well. If the distance is half as much, the force is going to increase by a factor of not 2, but 2 squared, or 4. For the second question here, we want to know what happens when they are 1/5 of their initial distance apart. So same idea, we're going to set up our new equation once again. F prime, our charges don't change, so it's still k q1 q2 on top. And then r over 5 on the bottom, that quantity squared, which becomes k q1 q2 over r squared over 25. We multiply the top and bottom by 25 to get rid of that double fraction, and what we're left with is that F prime equals 25 k q1 q2 over r squared. We see here that that 25 is the key difference, and so our new force is 25 times our original force. Once again, that makes sense if we think about the concepts of an inverse square law. All right, we have a diagram over here showing an arrangement of charges, 4 charges specifically, A, B, C, and D, and we want to figure out the magnitude and direction of the net force on charge A. So we know that charge A, charge B, and charge D, or charge C, all have a charge of plus Q. D has a charge of minus Q. So the first thing I'm going to do here is I'm going to think about object A and just think about the forces that are acting on it. Okay, so object A is going to be repelled up by object B. We'll call that FB. Object A is going to be pushed down by object C, because that also repels it. And it's going to be attracted to object D. So we're going to have FD going that way. What I'm going to do now is I'm going to calculate the force from each one, and in each case we're going to be thinking about Coulomb's law, k q1 q2 over r squared, and we'll go from there. So for the force from B, let's start with that, the force between A and B here. it's going to be equal to K times Q over 2D, that quantity squared, and this simplifies to KQ squared over 4D squared. Okay. For the force from C, okay, FC, that is going to be equal to K times Q just over D squared, okay, or KQ squared over D squared. And for the force from D, it's going to be KQQ. We don't have to worry about the sign there because we already dealt with the sign in terms of our direction, all over D squared, and so we get KQ squared over D squared. We're now going to think about the net force in both the x and the y direction. So in the x direction, we just have FD, which is KQ squared over D squared, and that's going to be going to the right. In the y direction, okay, we're going to have FB going up, so that's going to be KQ squared over 4D squared. And then we're going to have force of C going down, so KQ squared over D squared. I'm going to go ahead and multiply top and bottom by 4 to give this a common denominator. And since it's going down, it should be negative. And so we end up getting a net force here of negative 3KQ squared over 4D squared, which just indicates that it's going down. We can then go ahead and combine those two forces. So those two vectors combine like that, and then our overall is going to be going down at an angle, something like that. And so we can then use Pythagorean theorem to get the magnitude here. So KQ squared over D squared, that quantity squared, plus 3KQ squared over 4D squared, that quantity squared, equals C squared. And so we end up getting K squared Q to the fourth over D to the fourth when we square that first term, plus 9K squared Q to the fourth over 16D to the fourth. It's equal to C squared. Two things we can do. Number one, we can find a common denominator here, so multiply that one top and bottom by 16, and we end up getting, when we combine those, is 25 K squared Q to the fourth over 16 D to the fourth equals C squared. We take the square root of both top and bottom, and we get that our hypotenuse C here is equal to 5KQ squared over 4D squared. The other thing we can do is solve for the angle, so I can say that tangent of that angle equals opposite, which is 3KQ squared over 4D squared, solving for this angle here, divided by adjacent, which is just going to be KQ squared over D squared. A lot of things actually cancel out here. And it ends up being that tangent of our angle is just equal to 3/4, and so our angle, when we take the inverse tangent of both sides, is going to be 37 degrees. So it's if we're looking for our overall answer here, our force is going to be equal to 5KQ squared over 4D squared at an angle of 37 degrees south of east. Of course, you could have solved for the other angle, and then you would have gotten 53 degrees east of south. So for this problem, we have two arrangements of charges, and in each case, we want to rank the net force on each of the charges in each arrangement. So I'm first going to just think about the direction of the forces on each one. And so for the first arrangement, A and B are oppositely charged, so they're going to attract each other. Okay, A and C are the same charge, so they are going to repel each other. And then lastly, B and C are also oppositely charged, so they will go ahead and attract each other. So we see here that all of these have two forces going in complete opposite directions. So the directions alone don't necessarily help us. But what I can also do, though, is solve for each force. And in order to do that, I'm going to be thinking about Coulomb's law at each time, k q1 q2 over r squared. And so I'm going to write out an expression for each force, starting with the force between A and B. Both charges there are just q, so that becomes q squared. And the distance, I'm just going to say that's 2, because they are 2 blocks apart, so 2 squared, and we get kq squared over 4. For the force between A and C, it's going to be k times 2q squared, okay, because C here has a charge of 2q, over the distance between them, and that's going to be 6, that quantity squared. So we end up getting 2kq squared over 36. Obviously, we see mathematically here how that distance really makes a big difference since that term is squared. And then we have the force between B and C, and that's going to be k times 2q squared once again over 4 squared, or 2kq squared over 16. Now that we have that information, what I would look at here is this, the force between A and B, is clearly the strongest force. So these two forces are the strongest. But A has a much weaker counterforce here. So FAC, which opposes that force, is weaker than FBC. And so that means A is actually going to be our greatest one. And I know we're going from least to greatest, but I'm just going to put that at the end. We know that A is the greatest one. B then is going to be the second greatest one because it has the biggest force acting on it, and this force of BC opposing it. And then if we think about C, it has the 2 weakest forces acting on it, and they're opposing each other. So the net force on C is actually going to be smaller than those 2 forces, and so C actually ends up being the smallest. For that second situation, I'm going to start off the same way, just identifying the direction of the forces. Okay, so for object D, it's attracted to object E, so FDE is going like that, and going to the left there on object E. Object D is also attracted to object F, so the force of DF is pulling objects D and F together. And then lastly, we have the force of EF, all right? Those objects repel here, all right? And so we have forces that look like that. So the first thing we can do, and this one we can actually get one conclusion right off the bat, we know that F is going to be the smallest because it has 2 forces opposing each other. All right, whereas the other 2 objects have each one of these forces, but they're combined with another force. So the next thing then we want to think about is these 2 forces, FDE, are the same for both. The only difference is the one object D, has this force FDF, and object E has that force FEF. So let's think about the magnitude of those 2 forces, because that's really all we need to determine here in order to solve this. So the force between D and F is going to be kq squared. Distance between them is going to be 6, so over 6 squared, or kq squared over 36. The force between E and F is going to be kq squared, but the distance there is only 3, so kq squared over 9, all right? And so that means that the net force acting here on object E is actually going to be stronger, okay? It has this force FDE, just like object D does, but this extra force that's added to it, FEF, is bigger than the extra force added to object D, FDF. And so our ranking is going to go F is less than D, which is less than E. Let's go ahead and work through this next problem here. So what we have are 2 charges. For set 1 is positive Q and negative 2Q, and we want to place a third charge somewhere so that the net force on the third charge is 0. We want to know, should that third charge be placed to the left, to the right, or in between the 2 charges? So I think the easiest way here is to actually just go through and try the different locations and see which one works. So let's start with the middle, and let's say we have a positive charge here. We don't actually know the sign of that third charge, but let's assume it's positive. Let's think about the direction of the forces. Well, it's going to be repelled from this charge on the right, or on the left, and it's going to be attracted to this charge on the right. So that doesn't work, and if it was negative instead, okay, what we would see is just the reverse. It would be attracted to the charge on the left, repelled from the charge on the right. So that's not a possible location because we need the net force to be zero. And if the net force is going to be zero, it means those forces have to go in opposite directions. So let's try over here on the right-hand side. Okay, if we have a positive charge, it's going to be attracted to Q2 and repelled from Q1. So that possibly could work. If we try on the right-hand side, and we have a positive charge, it's going to be repelled by the Q1 and attracted to Q2. So that also possibly could work. So the other thing we need to keep in mind here is not only do these forces have to go in opposite directions, but they have to have the same magnitude if they're going to cancel out and lead to a net electric force of zero. So thinking about Coulomb's law and what that force depends on, we know that that force is directly proportional to charge and inversely proportional to distance. So if we think about this case over here, the distance for the 2Q charge is smaller than the 1Q charge, right? And so we have a bigger charge closer, all right, and a smaller charge further away. So there's no possible way that F2 and F1 can be equal, all right? F2 has to be bigger than F1 because the charge is closer and the charge is bigger. So that means that that is not a possible location, and this here must be the correct location. It must be placed to the left of the two charges. Moving on to part B, I'm going to consider the possible locations for this charge. Once again, I'm just going to consider the positive charge, but as we saw in part 1, if we change the sign of the charge, it doesn't necessarily change which location works, it just flips the direction of the two forces. So let's think about this location here. We'll call this 1, we'll call that 2. If we have a positive charge out here, it's going to be repelled by both of those charges, and so that doesn't work as a location. And the same thing could be said if we're out here. It's going to be repelled by both of those, and so that doesn't work. If it was negative, both would attract and both would go in the same direction. So that must mean it goes in the middle here, and we see that that will work. The charge 1 is going to repel it that way, charge 2 is going to repel it that way. Thinking about the amount of force once again, we do know it will have to be closer here to charge 1 because charge 2 is a stronger charge, but that's completely possible being in the middle. So our answer here is going to be in the middle, in between those two charges. Moving on to part C here, we actually want to mathematically solve for the distance from the third charge to Q. So this distance here, which I'll call x1, all right, in terms of d. I'm actually going to name this distance here also to be x2. We could say that it's d minus x, but as you'll see in a second, it's going to be a little bit easier if we just leave it as x2. So I'm now going to set up Coulomb's law. I'll set up an expression for the force from each one. So the force from charge 1 is going to be K times Q times Q3, which is that third charge there, all over x1 squared. The force from charge 2, the one on the right, is going to be K times 4Q times Q3, all over that distance, x2 squared. Now we know that those two forces must be equal to each other in order for this to work. So I can say KQ times Q3 over x1 squared equals, and I'll pull the 4 out here, 4KQ Q3 over x2 squared. I'm going to go ahead and cancel out the Q's and the K's and the Q3's, all right, and what I'm left with here is 1 over x1 squared is equal to 4 over x2 squared. I'm going to go ahead and cross multiply this here, and what I end up getting is that x2 squared equals x1 squared times 4, and I'm going to go ahead and solve then for x2 in terms of x1, and we find that x2 is going to be equal to 2x1. All right, so maybe you see exactly what this is going to end up being, maybe not, but we now know the ratio between those two. We know that x2 is equal to 2x1, and we also know that x1 plus x2 must equal d. All right, and so I'm going to just substitute in here, and I'm going to say x1 plus 2x1 is equal to d. So 3x1 equals d, which means that x1, the distance from charge 1, is just d over 3. x2 then would be 2d over 3. All right, and that works twice as much. So it's going to be 1/3 of the way from here to here. And there's your final answer.